Already a very nice introduction to the neutron diffraction and a tutorial on the use of full prof. He already told us that his interest was concentrating on magnetic materials, and indeed today he will tell us about powder diffraction and magnetism.
Okay. Okay, thank you for the introduction. I'd like to thank the organizer again. It's better and better after every day and night. So today I will do the second part of the lecture on neutron powder diffraction, and we will talk about pretty much only magnetism today. So as I said the other day, this is most of what I'm doing is related somehow to magnetism, and in particular frustrated magnetic system that sometimes do not order. But today we'll talk about systems that do order magnetically, and the powder diffraction, neutron powder diffraction analysis of such state. So I realize that in the audience, probably a lot of people are not at all familiar with the subject and with this topic. And therefore, I'll start with a very general introduction and very simple introduction on the different type of magnetic orders, just so that everybody is up to speed with that. I will explain how we can describe, in general, very complex arrangement of magnetic moment by the formalism of propagation vector, which is one of the most useful. Formalism is used a lot by physicists. You can use also 3+D superspace symmetry, but this is not generally the most used formalism. Then we'll see magnetic structure factors and how do they enter, is the neutron intensity for magnetism is related to the magnetic moment. And then we'll go through two examples of what are magnetic structure determination, one of them using symmetry and the other one using simulated annealing. And then we will see beyond that, what is it that we can do in case of more complex problems, maybe not limited to powder diffraction, but in general. So as I mentioned the other day, just after the war, this is the work from Clifford Shull at Oak Ridge. And this is one of the first, as you can see, a two-axis diffractometer here in 1945. This is the first pattern obtained on manganese oxide, which is an antiferromagnet at low temperature. So this is here, you can see the resolution at the time was not so good. This is the diffraction pattern coming from the nuclear scattering alone, so this is at room temperature. And as you cool down the sample, in this case at nitrogen temperature, at 80 Kelvin here, you can see all this new reflection, which are actually purely magnetic reflection coming in. And the first thing that is quite important to notice is that you can see that the intensity of this reflection is not at all negligible with respect to the nuclear scattering. So the magnetic cross-section is a relatively large quantity for neutron scattering. And from this, he was able to determine the magnetic arrangement in this system. It's a very simple antiferromagnet. So in general, and this is very, very simple, and I apologize for some of you that maybe have a lot of knowledge in this area, but in crystal, some of the atoms and ions have unpaired electrons, and typically transition metals or rare earth ions. And the intra-atomic electron correlation Ohm's rule favor always a state which has a maximum S or J, whether S or J is the relevant quantum number. And you have a magnetic moment in such case which is proportional to the spin or to the total orbital momentum and related by the Lambda factor. Now, when these atoms are positioned in solids, there's a whole range of different interaction, magnetic interaction that can happen. The most simple one is considering the direct overlap between orbitals, for example, 3D orbitals or 4D orbitals, what are even more diffuse. And you consider the overlap of this wave function and the spin on each of the magnetic center will tend to align ferromagnetically or antiferromagnetically depending on the distance and the overlap. You have also indirect exchange interaction where essentially you have a transfer from one of the magnetic center to the other magnetic center through ligands, for example, oxygen, and this is usually called super exchange. You can have longer pathways, like through 2 oxygen super exchange. You can have very long exchange pathways, for example, in organic, in molecular magnets. And this is essentially coupling here, so you have a Hoppening integral between the 2 magnetic center. In metals, the magnetic moments that are localized sometime on actinides or even on simple metals, the localized magnetic moments are coupled through coupling with the localized electrons. So with essentially conduction electron, and this is another type of exchange interaction which essentially is more complex. It's modulated in space and also the sign changes as a function of the distance. And finally, you have exchanges such as dipole-dipole interaction. This is much weaker than any of the other interaction, which means it's relevant only at very low temperature and when you have large magnetic moments. Anyway, the reason I'm saying all this is that, in general, the form of the Hamiltonian is not known, and it's very rare that you will have an ab initio calculation that will tell you what is a magnetic ground state. In metals, it's really, really difficult to determine what will happen, and you can pretty much guarantee that any calculation will be wrong, which means the magnetic structure that is determined is different from what is predicted. And so the magnetic ground state is usually determined experimentally from different techniques, and neutron partner diffraction plays, obviously, a big role here. Now, to take a very simple picture, at high temperature, you have a paramagnetic state. So you have magnetic centers bonded and so on, but phenomenologically we can say that these magnetic centers are connected with different type of interaction. This is the simplest form here, an isotropic exchange Hamiltonian. And essentially at high temperature this spin or this magnetic moment fluctuates in all possible directions of space. So this is like a magnetic gas. So the expectation value or the average value of the spin is essentially 0 in this state. You have no long-range correlation. As you cool down, obviously, the system gains energy from the magnetic exchange interaction, and at a certain temperature, Tc, critical temperature, the system goes in an ordered state, which essentially, in complete opposite to the previous state, in this particular state, then you have a quasi-static configuration of the magnetic moment, which means that the expectation value of S is now finite, it's different from 0, okay? So of course that's very trivial here. And why is this important? Oh, one of the pictures didn't show up, I'm sorry. So what is important? That's the one from Bill David. We've already seen it on WBCO. So of course there's a lot of materials where knowing the magnetic state is extremely important. For example, in molecular magnet, whether they are single molecule magnet or extended network, these are very important systems with potential application in a range of fields, for example, quantum computing and so on. In multiferroics, or what I prefer to call spin-driven ferroelectric, you have systems that become electrically polarized only when they're magnetically ordered. And essentially, the origin of the electric polarization is the appearance of a long-range magnetic state. So in order to understand this system, you need to understand the magnetic ground state. Otherwise, you have no idea of what's happening. And of course, in superconductivity, for example, in particular, unconventional superconductors where superconducting ground state always appear relatively close to a dome in the doping regime where you have antiferromagnetic spin fluctuation. Okay, the one thing that is important is that, like any other type of structural phase transition, or phase transition in general, this is a spontaneous symmetry breaking process. So if you imagine that the structural phase transition corresponds to a condensation of a soft mode, exactly in the same thing for magnetism. For magnetism, this is a spontaneous symmetry breaking process. And it's not always obvious, especially in the case of ferromagnetism. If I take a crystal like that, and these are my magnetic center, and I develop a long-range ordered ferromagnetic state, you can see that I have not changed any of the periodicity compared to the nuclear state, right? There is no new periodicity in the structure. So, but there is one important symmetry operation that you have lost. It's time reversal symmetry. This is usually a symmetry that if you are a chemist and you're doing structural work, you will usually not consider this symmetry at all because it's actually irrelevant for polar vectors. But here, this is not irrelevant. So if you cool a system that becomes ferromagnetic, you have two possible ground states, in this case of a very simple Ising magnet, that will be related by the moment pointing up or pointing down. And these two things is in itself spontaneously symmetry breaking of time reversal symmetry. Okay. So you can analyze all this magnetic phase transition in the same context that you do with all the other ones, which mean in the framework of Landauer theory of phase transition and so on. Now, one thing to remind you very briefly is that the reason for that is that magnetic moment, classically, you can describe them by a current loop, right? So the very classical description of an orbital momentum here. Okay, and for example, when you apply inversion symmetry to a normal polar vector, this quantity is parity odd and time even, which means that if you apply inversion symmetry, you reverse the polar vector. If you apply time reversal symmetry, it does nothing on a polar vector, on a structural displacement, for example. For magnetic ordering, you have to consider the effect of time and parity differently, in the sense that if I reverse direction of time, I reverse direction of the loop, and therefore I flip the moment. Okay, so that's a very different symmetry when you deal with magnetism. We don't have time to go into details of that, but I thought it, for people that start in the field is what the most important thing to do. You have to consider the symmetry of the magnetic ground state, and without considering this particular symmetry element, which is time, you will never be able to understand what's happening. And this is highlighted here in a mirror. So with axial vector, which is what we call them, or we call them also pseudo-vector. Some people call them dishonest vector, because it doesn't behave like you think it's going to behave. So for example, if you take a mirror here, a mirror symmetry, and you consider spin, then mirror symmetry with a spin contained in the plane of the mirror will flip the spin, which is the opposite of what you used to. And you can do that yourself if you spin in front of a mirror like that. And you look at your image, you will see that it's spinning in the other direction. This one is a bit more difficult to do. You have to lie like that. So if you have masala tonight and you'll be drunk, you can ask a couple of friends to rotate you this way. But you see that, for example, magnetic moment, which is perpendicular to the mirror, the effect of mirror symmetry doesn't change this particular magnetic moment. So just a brief note before going further. So what type of magnetic order do we have? Well, the simple one, it looks like this slides are all shifted, but I guess you can see enough to understand. So for ferromagnet, very simple. So the magnetic moments point all parallel to each other. A very simple collinear antiferromagnet here. So they are antiferromagnetically, first neighbor are all antiferromagnetic. And now you have much more difficult state. For example, modulated structures. So this one is an example where you have essentially the size of the moment, the size of the ordered component of the spin or the orbital component is modulated in space. And this can be longitudinal modulation where the amplitude changes as you move from unit cell to the other. And this one is exactly the same way, but it's transverse. So here the direction of the spin is perpendicular to the wave vector. And this one is parallel to the wave vector. And then you can have state where the magnetic moment doesn't change in magnitude, but change in angle. So these are essentially spirals where the moments rotate perpendicular to the q vector. And then cycloids where the magnetic moment rotate in the plane of the modulation and things like that. And then any possible combination of this state. So you can have very, very complex magnetic state. A very famous example is the conical structure, which is, to describe it, you need two different wave vectors. So you need, a conical structure can be represented as a rotating component, which forms a spiral, and then a ferromagnetic component that is perpendicular to the plane of the spiral. And this is a very simple metals, for example, like holmium, metallic state ordered in this particular spin configuration. Okay, so typically in the neutron diffraction pattern, if you have a simple ferromagnetic material, what you will see is that on top of nuclear reflection, you will have new peaks. Of course, if you have a ferromagnetic material, you don't break any any translation of the Bravais lattice that you had already at high temperatures, so these peaks are on top of the existing nuclear peaks. And in the case of an antiferromagnet, then this peak will obviously be at different position in Q space, which means different position on the diffraction pattern. Okay, so the entire question is, Bill was talking about parametric studies yesterday. This is an example of two parametric studies in some of the multiferroics. And you can see here the magnetic peaks. So all this new reflection that appears on cooling, these are purely magnetic signal. And you can see sometimes very complex, as you continue to cool down, a very abrupt change in the position of these peaks, which means a very abrupt change in the periodicity of the magnetic lattice. Okay, so how do you go from this to the magnetic structure, which in this case at low temperature is extremely complex? It's essentially an elliptical modulation of the moment along complex zigzag chains in the system. So how do you go from that to that is the question. So in order to do that, we need to briefly describe all the steps. And the first one is how do we describe this structure, and that's probably very easy to understand, I hope. So essentially, you take a crystal, you consider the magnetic center alone here on this graph. You have, for simplicity reason, only one atom per unit cell. And the atom in the unit cell translated by the RL, lattice translation, plus RJ, fractional translation, will be essentially labeled by these two index, L and J. So L is the pure lattice translation, and J is the fractional translation in a unit cell. So you can label all of your spin in your system MLJ like that. Okay? So what you do is for all this spin, you essentially do a Fourier, you take the Fourier component instead of the magnetic moment itself. So you will say that a magnetic moment, which is a vector quantity in the unit cell number L, and for the atom J, at the position RL, will be the sum on all the possible wave vector that describe your modulation. So you can have more than one in principle of the Fourier term. So that's now a complex vector. So this is a real vector. This is a complex vector. And then a phase, which depends only on the position of the atom with respect to the zero cell. And one important condition, if you have a single wave vector, which is, I have to say, most of the time is true, is that because the M quantity is a real vector, you need to impose this particular condition, of course, that the Fourier component of vector k is the complex conjugate of the 1 minus k. So essentially, for a single k vector, you will describe it like that. And this simplifies a lot the formalism of describing complex structures. For example, a structure that will rotate in the AB plane will be simply the linear combination of two vectors, one that is real along A, let's say, and another vector that is purely imaginary along B. Okay, and this is also decomposing like that. It makes it very well adapted to representation analysis, which is of course something happening in complex space. Now, magnetic structure factors. So you describe your magnetic structure. You can describe pretty much everything with this formalism. Now, the magnetic structure factors we've seen the other day. We've introduced the cross section and for nuclear scattering. So for magnetic scattering, let me remind you, I had this slide already on the first day, that the neutron has a magnetic moment, and this magnetic moment is tiny because it's a nuclear spin. And so the nuclear magneton here is about 3 orders of magnitude smaller than the Bohr magneton. So this is a tiny moment. But even though it's tiny, the magnetic cross-section is typically as large as the cross-section for nuclear scattering. So in order to calculate the cross-section, you have to consider a neutron. For simplicity, a unique n-pair electron here and a position vector between the two. And you write the vector potential, the magnetic potential imposed by this moment at the position R. And you can calculate the magnetic field by taking the curl of this potential vector. And then the potential interaction is just the scalar product of the spin of the neutron by this field. And if you do all the mathematics, I will not go through the detail, what you find is that the cross-section for magnetic scattering is proportional to this, what we call the length of the magnetic interaction vector. And I will explain that in a minute. So if you take, that's going to be more difficult now for this slide. So you have to have a little bit of imagination. I don't know why everything is shifted today. So this is Q. This is your scattering vector. Okay? Like in the case of nuclear scattering, you're going to construct a magnetic structure factor, which is essentially the Fourier transform of your magnetization density in real space. Okay? So M of R is a vector. So that's different to what we've seen so far, where the scattering lengths were scalar. Now this is a vector quantity. And the Fourier transform is a complex vector. Okay? So now you have M of Q, which is a complex vector. You have Q, the scattering vector. You take the projection of M of Q perpendicular to Q, which is the scattering vector. You find this term that we call M perpendicular to Q. This is itself a complex vector. And now you take the norm of this complex vector, and that's your scattering intensity. And what it means is that it's very simple. If you have a magnetic moment that is in the same direction as Q, then the projection perpendicular to Q is 0. So you have a very strong extinction rule with neutron that if the moment direction is parallel to Q, then you have absolutely no intensities. And that's the only directional information that you get in this problem. The problem is more complex, of course, than in the terms, this thing is a vector quantity. And determining the magnetic structure means determining this vector quantity. Okay? And of course, the only information now that you have is this projection perpendicular to Q, which sometimes is very good for very simple structure because you have very strong extinction. But for very complex structure, it's a big problem to go back to the magnetic configuration. Okay. Now, one important thing is I treated only the case of spin here of the electron, but of course there is also the orbital momentum. And in general, I will not go through the maths, but you can rewrite the cross-section in the case of spin and orbital contribution. In general, unless you apply very clever technique with non-polarized neutron, and this is certainly the case for powders, you cannot separate the spin and orbital component, which means that the expectation value of your measurement is L plus 2S. This is the full orbital momentum. There are other techniques such as X-ray magnetic scattering where you can separate the spin and orbital momentum, but with neutron this is not something you can do. So if you have a rare earth element where J is the right quantum number and it's very large, like I don't know, J called 9 or something like that, then 7.5 or 8.5, then you will have the full J in a neutron scattering cross-section. Okay, so the quantity of interest for us, crystallographer doing magnetism, is this quantity, which is very similar to the structure factor, the unit cell structure factor that you are used to, except that here we have our Fourier component, which are, I repeat, complex vectors. You have your phase term, and then you have a form factor. So you remember for nuclear scattering, we didn't have a form factor, because we said it was a very short, a very narrow Fermi pseudopotential, and therefore it was constant in Q space. But now we have a form factor. The difference between structural determination and magnetic structural determination is that usually we know where the magnetic atoms are, because we know what's happening in the paramagnetic phase. So this phase itself is already known. The problem is not so much to determine the phase, it's to determine the amplitude, which is the reverse problem of what you do usually in conventional structural analysis. So now I'll go back to the form factor. I mean, obviously, the interaction between the neutron and the ampere electron is very different. Now we're talking about scattering from electrons, not the nucleus anymore. And that's essentially exactly equivalent to what happens with X-ray. So with neutron magnetic scattering, you will have a form factor that falls off very rapidly. And don't forget that when in your structure factor, it comes as a square, because the intensity is proportional to the Fourier transform square. So you will have exactly the same form, and this is tabulated, essentially typically calculated from single orbital contribution using Bessel functions. So the magnetic cross-section decreases the modulus of Q, and I will want to illustrate that in this particular example. This is one of the system, again, this doesn't show, I don't know why. So this is typically, this will be a Q of 4 or 4.5. And this is probably, I would say, something around 0.3 or something like that. So you can see this is the neutron diffraction pattern. The black line is the total scattering, so nuclear plus magnetic, and the red line is purely magnetic, which I've highlighted in this color. So you can see that as you go to IQ, there's almost no scattering left, okay? Which means that we have very little information usually